pre-algebra. This will be lesson 9.1, so representing patterns. We're getting into writing expressions here. Some things we want to be able to do is identify and represent patterns using models, tables, and expressions, and then write and evaluate algebraic expressions that represent patterns with constant differences. Okay, so let's take a look. Here's an example here. Patterns have definitely been something people have studied for a long time. Legend has it here that Pythagoras, so Pythagoras was a guy who he made a big theorem back in the day about right triangles. A squared plus b squared equals c squared, the side lengths in right triangles. So if you're not familiar with that, you'll definitely be seeing that coming up sometime here. But one pattern that they studied is shown below. So we see figure 1 with the 2 dots there, then figure 2 and figure 3. So let's just draw a couple more. So for the fourth figure, if we look at the pattern here, it looks like they all have 2 rows, but the number of dots in each row is increasing. So in the fourth one, we should have 1, 2, 3, 4, and then 1, 2, 3, 4 again. In the fifth row, 1, 2, 3, 4, 5, and then another 1, 2, 3, 4, 5. And in the sixth figure, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so let's see if we can organize this information into a table and kind of dive into it a little more and see what might be really going on here. So the figure numbers, again, are just going to be 1, then 2, then 3, 4, 5, 6, and so on. And now the number of pebbles, if we look at this first figure, there are 2. Okay, in this figure 2 here, there are 4. Okay, then it looks like we have 6. And then in the ones that we drew, the fourth figure had 8, right? It was 2 rows with 4 each. The fifth figure was 2 rows with 5 each, so a total of 10. The sixth figure was 2 rows with 6 each, 12. And if we had to go 7th, what would you guys guess? 14? Okay. All right, so let's extend the pattern to determine how many would be in the 10th figure. So just looking at the pattern here, okay, if we were going to extend this out, so in the 7th there was 14. In the 8th row then there should be 16. In the 9th row should be 18. So in the 10th row we would expect there to be 20 pebbles. Okay, so let's describe the patterns we see. And basically in words. Okay, so to me, it looks like in the figures we were talking about having 2 rows, right? Each figure has 2 rows, and the number of pebbles per row is just kind of increasing by 1. Okay, and it also looks like then from the table, if we take a look, it appears that to get the number of pebbles to go from one to the next, there's this constant pattern of just adding 2 over and over and over, and that's what we're seeing in the rows as well, or in the figures as well, I should say. Okay, so could we then figure out how many pebbles are in the 53rd figure? Okay, would we really need to extend our table, or would we need to draw all 53 figures? Or can you kind of see a sort of relationship going on with these values? Okay. So if you remember, we talked about each time you add a new figure, it's just adding 2 more dots, right? Because it's adding 1 to the bottom row and 1 to the top row. So really, it appears that the number of pebbles is always just 2 times the number, the figure number. Okay, so if we were in the 53rd figure, if we just were to multiply that by 2, I would expect there to be 106 pebbles in there. Okay, because again, if you take a look at these values, they are always just equal to the figure number times 2. Okay. Can we write a numeric expression using the number 3 for the number of pebbles in the 3rd figure? Okay, so in the 3rd figure, the number of pebbles in the 3rd figure, we knew the 3rd figure had 6 pebbles, so an expression, how did we get 6, basically? We were taking the figure number and timesing it by 2. So it would be 2 times 3. That would be a numerical expression. Okay, 2 times 3. We're using the number 3, and we're just multiplying it by 2. All right, let's keep moving. Can we write a similar numeric expression using the number 7? Sure, right? Isn't the number of pebbles always just equal to the figure number times 2? Okay, so let's get a variable in the mix here. Okay, let's let n represent the figure number, right? A lot of times you use n for number. Let's use n to write an expression that could be used to determine the number of pebbles in figure n. Okay, so n again is a variable. If we think about our table from the front, n was here, and then the number of pebbles was here. Okay, in the first row there was 2, in the second row there was 4, the third figure there was 6. So the question is saying in row n, okay, a variable, anything, what could we do to get the number of pebbles? Well, aren't we just timesing 2 by whatever n is? Okay, 2 times n, 2n. So what value would you substitute for n to determine the number of pebbles in the third figure? Okay, well, if n is the figure number, and we're talking about the third figure, we would make n equal to 3. Okay, and we could plug in a 3 right there. 2 times 3 would get us the 6. Okay, can we check to see that our expression from part A is correct by evaluating it? Okay, to evaluate something, we're just figuring out its value. Okay, over here's a definition. We're not solving anything. We're just figuring out the value. If we were to plug in the n of 3 right there, it would end up being 2 times 3, and we would evaluate that to be 6. Okay, and this kind of verifies what we had saw before. In the third figure, the number of pebbles was 6. Okay, can we use our expression to determine the number of pebbles in the 100th figure? Sure. N would just be 100. Okay, the figure number would be 100. 2 times 100, of course, is 200. All right, let's take a look. Here's another pebble arrangement shown below. Okay, different pattern. Let's see if we can get this one investigated a little bit here. So figure 4, again, so if n equals 4, the fourth figure, take a look at this pattern. We start out with just the 1 dot here, and then they add 1 on the top and 1 on the side. Then they add 1 on the top and 1 on the side again. So figure 4, we would have the previous figure, like that, and then we would add 1 more and 1 more there. Okay, n equals 5, we would have the previous pattern of 1, 2, 3, 4, 1, 2, 3, 4, and we would add 1 more there and 1 more there. Okay, figure 6, we would have the previous pattern of 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and we would add the 6th one there and there. Okay, so let's see if we can get this into a table form and then take a look at the difference in number of pebbles each time. Okay, so in the first figure, there is just 1 pebble. Okay, let's do this first. In the second figure up top there, how many total pebbles are there? There's 1, 2, 3. Okay, in the third figure, let me move this down a little bit. In the third figure, there are 1, 2, 3, 4, 5 pebbles. Okay, in the fourth one, there are 1, 2, 3, 4, 5, 6, 7. In the fifth figure, there are 1, 2, 3, 4, 5, 6, 7, 8, 9. In our sixth figure, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so those are the ones we've drawn. Okay, do we see a distinct pattern going on here? Okay, what does it appear is happening? Let's fill in the number of pebbles first. Okay, it looks like it's going from 1 to 3 to 5 to 7 to 9, and that should make sense. They're adding 2 because we're just adding 1 to the top and 1 to the side. So it appears as though the pattern would continue and the number of pebbles would just go up by 2. Okay, and that's what they're talking about in this right column here, the difference in number of pebbles. So this first one, there was nothing to start with, but to get from 1 to 3, what was the difference in number of pebbles? It was 2. To get from 3 to 5, what was the difference? 2. To get from 5 to 7, 2. Okay, so that common difference of 2 is gonna stay constant, right? That's what it means to be a common difference. It's the same all the time. And note, one other way to get that difference usually refers to subtraction, is you can take any term and minus the term before it, and it will give you the common difference. All right, so any patterns we observe in the pebble drawings and the table above? Well, yeah, for sure. We noticed that we are adding a dot to the top and a dot to the bottom right there. So that's why we're adding 2 when we draw them. And that's also why the pattern is showing in the table that we're adding 2. Okay, so number 15 here, subtract consecutive terms. That's what I was just kind of alluding to here. If we subtract consecutive terms, okay, so consecutive means one after another. So for instance, if we subtract 19 minus 17, we're going to get a value of 2. Okay, if I do that again, different terms, if I subtract 17 minus 15, okay, we're going to get 2. So we're, again, getting this constant difference because that's the amount of change that's happening to get from one figure to the next. Okay, so how does this constant difference relate to the pattern we observed? It's exactly the same thing, right? It's showing how many pebbles are being added in each term. All right, so let's keep investigating this a little bit here. So the number of pebbles in a specific figure can be written using repeated additions of the constant difference. So for example, the third figure is 1 plus 2 plus 2, okay? Because again, what we had originally, there was 1 pebble in the first figure, and then we added 2 to get to the second, and then 2 more to get to the third. Okay, so all that is saying, or another way to write that, okay, is if you recognize right here, when we add this 2, we are actually adding 2 twice. So it could be written that way, where it's saying it's 1 plus 2 2's, or 1 plus 2 times 2. Okay, so if we look into the table here, okay, and again, the figure number is n. Okay, in the first row here, in figure 1, we only had 1 pebble. But in figure 2, we had that same 1 to start with, but then they added 2. So here we can see it was written as 1 plus we added 2 one time. Okay, in the third row, we had the 1 original, then we added 2 again to get the second row, and then we added 2 a second time. That's why we said it can be written as 1 plus 2 times 2. Now in the fourth row, we would have the original 1 plus the 2 we added to get to the second row, plus the 2 to get to the third row, plus the 2 now to get to the fourth row. We could write that, let me zoom in and give myself some room here. We could write that as 1 plus 2 3 times. Okay, because we started with the 1 and we added 2 3 times. Okay, in row 5, we had the original 1 plus 2 to get to the second row, 2 to get to the third, 2 to get to the fourth, and 2 to get to the fifth. So that's really 1 plus 2. We added 2 in this case 4 times, right? We see the 4 times that we added 2. 1, 2, 3, 4. Okay, so write the number of pebbles in the fourth and fifth figure using repeated addition of the constant difference. So we just did that, okay? We did that in the table there. Let's think about what's going on. Can we let n represent the figure number? Okay, we kind of already have that set up, right here. Can we represent, or can we use n to write an algebraic expression, okay, that could be used to determine the number of pebbles in figure n? Okay, so again, if this thing kept going and we eventually got to n, you know, we want n to be a variable. It could be 100, it could be 60, it could be whatever. I want some sort of shortcut formula. I want to be able to do it this way to figure out the number of pebbles instead of having to do it this way. Okay, and do it the long way. So what I want you guys to take notice of, In each case, we're starting with 1, because that's how many was in the first row. Now we are adding 2. For example, in the second figure, we added 2 once. Okay. In the third figure, we added 2 twice. In the fourth figure, we added 2 3 times. Okay. In the fifth figure, we added 2 4 times. So the number of times that you add 2 is always whatever n is minus 1. Okay, let's think about that. So the number of pebbles would always equal 1 that we started with, plus we add 2 n minus 1 times. Okay, and again, let's just think about that. Go back to, for example, right here in row 5. We started with 1, right? Always start with 1, and then we added 2 4 times to get the fifth total. So we started with 1, and we added 2 n minus 1 times. Okay? So what value would you substitute for n to determine the number of pebbles in the third figure? We would substitute 3 in for n. Okay, let's see if that's going to work out. Okay, part D, actually, they want us to do a different value. Check to see that your expression from part A is correct by evaluating it when n equals 5. Okay, so our n is 5. Oops, sorry about that. Make you guys dizzy. N is 5. So the number of pebbles in the fifth figure should be 1 plus 2. We can plug our n value in here. Okay. Which equals 1 plus 2 times 5 minus 1 is 4. We have to do the exponent or the parentheses first. Right? 1 plus 2 times 4, we need to do multiplying first. So 2 times 4 is 8. 1 plus 8 equals 9. Okay, so there should be 9 pebbles in that fifth figure. Okay, here's the real use of this stuff. Okay, can we use our expression to determine the number of pebbles in the 100th figure? Sure, okay, we could. This up here now is like a formula for us. Okay, it's the number of pebbles in the nth figure. So n is going to be 100. So the number of pebbles in that figure would be, if we plug into our formula, always with the 1 that we start with, we would be adding 2 100 minus 1 times, or 99 times. Okay, so 1 plus 2 times 99. Make sure we do the 2 times 99 first. Okay, 2 times 99 is 198. And 1 plus 198 is 199. Okay, so that's a fast way to get the number of pebbles by simply plugging in the figure number for n. Okay, and again, it's all based on the pattern of starting with 1, and then you're adding 2 n minus 1 times. Okay, let's just kind of show that pattern and why the formula works. Just one other quick example. Let's say, for example, we had a pattern like this of 3, 7, 11, 14, and it kept going. Okay. So in this case, we're starting with 3. That would be the first term. And the pattern, or that constant difference, is that we are adding 4. So I guess I made a typo here, right? This should be 15. Sorry, I was trying to make this up in my head. Messed it all up. All right, so we're adding 4, right? Okay, so the concept is, what if we want to get a term way out here, right? And we don't want to continue the pattern. Let's say we want to find the 20th term. Okay, so what that new formula was basically saying was, in this pattern, for example, we're starting with 3, and we are adding 4 each time. Okay, but here's the trick. To get, for example, to get the second term, we only added 4 once. Okay, to get out to this third term, we started with 3 and we added 4 twice. So to get out to the 20th term, we would start with 3 and we would add 4 19 times, okay, or n minus 1 times. Okay, and 4 times the 19 should be 76. And 3 plus 76 will get us a term way out here. The 20th term in that list should be 79. Okay, so that's the concept. It's always going to just be starting out with the first value, first term, plus whatever that common difference is. We'll just call that D times n minus 1. Okay, so hopefully that works. Hopefully you can see why that's working. And that is the beginning of finding patterns.